So, welcome to this webcast where we are going to talk about 3 different projects that we have been working on. This is all titled From Theory to Practice. So we'll talk about how do we get from the theory of AWS to practical implementations. As I said, 3 different use cases, 3 different projects from the field. So this is nothing that we made up, but the real stuff. What will those be? Number 1, we'll talk about data warehouse modernization with AWS big data solutions. Number 2, we'll talk about advanced analytics and complex event processing at a company called Kongstar. And number 3, we'll talk about stream analytics and machine learning with the so-called AWS OC, Opitz Consulting Quick Starter. Here we go. So what will we talk about in the context of data warehouse modernization with AWS? We'll talk about a little bit about the situation before we started this project. We'll talk about what did we want to achieve, what were the challenges, what did we as the consultants propose to our client, how did we end up with the technical implementation, and how did it all end, what's the takeaways, the results, and the outlook for the future. First off, what company did we talk to, or what company did we plan to work with in this case? We're talking about an insurance company, a mid-sized insurance company in Germany with around about 6,000 employees. They are serving approximately 4 million clients with approximately 14 million contracts, insurance contracts that they have. And their total yearly revenue is approximately 3.2 billion euros. So, as I said, mid-sized insurance company with an existing data warehouse. So years ago, they already started and implemented a data warehouse solution as a centralized data provider in their company for analytical and reporting purposes. They have a lot of standard reporting in place already. And naturally, being an insurance company, they also have done data mining in various ways over the years, actually for many years, decades even. But this has all been mostly based on Microsoft Excel, in some parts based on R or RStudio as a desktop version. So they're not entirely new to data mining or advanced analytics, predictive models, but they did not employ this on a larger scale up to now. So what did they define as their targets? First of all, it was really for them to get to know all of the technology, to kind of get a feeling for new technologies, especially everything that revolves around the Hadoop ecosystem. They wanted to learn the new approach or the typical approach to data processing when dealing with solutions based on the Hadoop ecosystem. Of course, for getting to know things, they did not want to invest a whole lot of money. So I guess a good description could be to take a big data test drive, so to really try things out, see how things work. And of course, beyond that, the motivation was or is to increase the flexibility for the data sources that they have, increase in variety of data sources, increase of volume in data sources, and the ultimate goal, or currently the far goal, I should say, is to enable their departments to self-service their analytical needs, but on a larger scale than what they've been doing so far. So, a couple of targets that seem quite reasonable, and since they haven't done much in this area before, the main part for them really was to get those points in bold typeface done during this initial project. And of course, with targets, there also come challenges. So what were the challenges in this case? First of all, they wanted to try out technology, but there was no specific, no concrete use case available, at least initially. They did not make any decision upfront regarding what products to use, what license model to go with, what deployment model to go with. So really very, very open, not to say undefined. As I indicated before, there were not much relevant experiences with the newer technologies based on the Hadoop ecosystem. And of course, as always, only little resources for actually driving this project in terms of personnel, but also no hardware available that they could readily use. And since this was really a kind of pilot for them, there was no detailed, no working integration between any, let's say, cloud provider and their existing networks. So the question was also, how could we get data into a kind of analytic platform? So with all this being said, we came up with a proposal to do a quick start based on cloud technology. So no hardware on-premise to be installed, no software on-premise to be installed, but really leverage the benefits of cloud deployment, which would allow for a small scale start, but also be able to accommodate growth if necessary, to have a wide variety of technologies at their disposal without having to prepare everything from scratch, without having to have administrative personnel available to take care of all of the operations. So have a wide variety to choose from, but not the need to take care of everything on their own. To be more precise, this proposal of ours came down to, for them, prepare an environment so they can easily start, to make sure that the employees are trained or educated as much as required, at least in the essential aspects of conducting this analytical project, and to be quite precise, to base all of this on AWS, because we felt that this is something that will fulfill all of the requirements that we talked about before already. So, technically, what is it? What did we choose? With AWS being defined as the basis for everything, of course, there are some logical choices, such as IAM for user management. Of course, that's the standard technology to use when dealing with AWS. Of course, for data storage, to go with S3. And since, as we said already, they wanted to have a variety of tools available, maybe even to try them out, it seemed reasonable to go with AWS EMR, Elastic MapReduce, as the basis for conducting this project, because it already comes with lots of different tools that you can readily configure at the click of a button. And the tools that were of interest in this case, just to name a few, was, for instance, Hive, Pig, Spark, of course, Python as a general purpose language, Zeppelin as a graphical front end, but also, since they had some experience, some previous experience already with R and the R programming language, we also decided to add RStudio into this mix. So this was mostly the technology, and to be able for them, for the client, for the users to quickly pick up on that and be able to use all of this, we created a series of mini tutorials for them to follow, so they could quickly carry out several steps in the tools that were mentioned here, so they would know immediately what to do to set them up, how to start an EMR cluster, what to do if I want to log on to Zeppelin, how can I access data in S3 from Spark, and so on and so forth. So in addition to the technological basis, a lot of the work was put into creating these tutorials so they could be distributed to a number of users, to really broaden the number of people that are competent in these technologies. Here's a sketch of what the technical architecture more or less looks like. As I said already, there was no direct network connectivity, so how to get the data into the S3 for analysis? We just uploaded flat files from different sources that we collected throughout the company, put them in several S3 buckets. And of course, from there, they were readily available in all of the tools that we mentioned already, in Pig, in Hive, in Spark, and so on and so forth. And front-end side, we try to approach this, as I said already as well, using Apache Zeppelin and RStudio, which were both installed either automatically on EMR or additionally by us in the case of RStudio, so they could be used by the clients accessed from their laptops, from their workspaces, and they could choose which one they, whenever they preferred. Here's a little overview of those mini tutorials that I talked about. So of course this is all in German, but hopefully not an issue. So we really went into details, into step-by-step descriptions. What do you need to do? So for instance, if you want to start an EMR cluster with a given configuration, then for instance, you could use the AWS command line interface, put in this command with all of those parameters, so just copy and paste, and as soon as you hit enter, the cluster will be started, and then of course afterwards you can find information about how to connect to it, how to use the tools. So as I said, really very simple step-by-step instructions that enabled basically everyone who was interested in trying things out and getting a first feel of how to work, how to operate on AWS and EMR. Yes, so this was really, as I said, indicated to be the initial project, the really first steps in AWS and Hadoop ecosystem technology. How did it end? Well, we achieved the targets. Everyone was happy. They learned really the basics, the basic ropes. During the runtime of this project, which was 3 months, we spent less than $500 in AWS resources. Of course, with a, let's say, a dedicated education of what to do and what not to do. Competency development was felt to be adequate for the time and for the time invested as well. And all of the people that were involved really felt that they had a better understanding of how things work and how you need to think in order to apply whatever approach you want to have to the AWS EMR technologies. Of course, we learned something as well. One important point for us was that we really want to focus on as few tools as possible, because otherwise you will simply get lost in the jungle of technologies and tools that are available. Of course, there can always be additional tools chosen if you feel that it's really good way to implement whatever you want. But especially as a start, it really seems to make sense that you stick to a few, so maybe 5 or 6, in order for people to still be able to keep track of what they are doing and also to distinguish between the different tools. The simple step-by-step tutorials was another point that we found to be important. So it doesn't have to be fancy. It doesn't have to be very complex. On the contrary, it makes sense to keep things really simple. Maybe include, let's say, 10 or 12 steps in a single tutorial, which will allow users to follow it, to really understand it, to maybe even repeat tutorials when they feel that they did not grasp everything on the first attempt. And so simplicity is king in this case. Last lesson that we learned was you need to have something in mind where you want to go, because if you don't know what you want, how will you know how to get there? So of course, it's always a nice idea to say, okay, we'll just get started and we'll just try out whatever we feel like, but it's always good to have a target in mind, a target architecture or a target, data structure, for instance, that you can then work on to achieve, even if it's not a real world scenario, but as long as it can be done with whatever you have, with whatever data you have, with whatever tools you have, then that's a very good approach to getting started, because everyone can relate to it much easier and feel at home much quicker. So this is the first report of our project number 1. Next up, we have my colleague who will continue.
Thank you, Roland. Hi, my name is Matthias Dickstahl. I'm developer at Opitz Consulting, and I want to talk about a project that we realized at Kongster. In the first part, I will talk about the motivation and challenges in that project. In the second part, I will talk about the basic infrastructure that give us the basics so that we are able to work. Afterwards, I give an insight into how to serve the data to the stakeholder. First of all, some words about our customer Kongster. Kongster is a mobile network operator headquartered in Cologne, Germany. The company is a subsidiary of Telekom Deutschland and founded in July 2007. They are specialized in discount mobile phone services marketed to younger people. By 2017, they had over 4,500,000 customers. Let's talk about the motivation to create a base for advanced analytics in AWS at Kongster and about the challenges we have to master. Further, we have to think about ways to improve the development processes. The big goal is to better understand the user and thereby to improve the user experience at Kongster. By enhancing the existing systems, we will to be prepared for future requirements and create now contents to reasonable time. Our motivations leads us to the challenges we have to master to achieve our goal. The basic task is to develop a basic system which we can use for advanced analytics in AWS. One side is to find right technologies in Hadoop ecosystems. On the other side, we have to find suitable AWS services. For people who are new in the cloud, the costs are a critical point. That's why we keep an eye on them and make them estimable. The provisioning of the cloud is an important task, which we should work out well. That way it makes it possible to use exact copies of the same infrastructure of used resources and services. Another point is that older systems are not able to process data in a reasonable time. By replacing them with the new technology, we are able to reduce the processing time and by that the working time as well. The secure data transfer is also a very important point. Tightened by the European General Data Protection Regulation, it got more important for data transfer between on-premise servers and AWS. We have to find a proper solution. While the implementation of the project, we have to live the agile method to determine problems fast and adjust the project plan if needed. After overviewing the motivations and challenges of a big data system for advanced analytics, we go to how to create the base for such a system. We look on how a basic infrastructure can be created and we can collect and process data with it. To create a clean infrastructure, we have to look at everything we need and how we connect the resources. Further, we have to think about a safe use of the resources. A good example are the security groups, which work perfectly if all the ports are open, but unacceptable user could access to the instance hosted services. To understand faster how the resources and services works, it's good to create them in the AWS Management Console first. There we can test the functions and use it as inspired for our CloudFormation template. The CloudFormation template's infrastructure has to be developed in JSON or YAML code. With this template, we are able to create multiple setup with exactly the same resources and services called stacks. This makes it easier to create an environment for development, test, and production systems. While the daily work, the templates can be used for faster and reliable provision of stacks. Further, the stacks can be updated and replicated easier. The changes for each task are made in the template code. The CloudFormation recognizes the differences between the old and the new code while generating the change set. In case of error, the rollback function will erase all changes. To achieve a secure connection between the created VPC and the on-prem system, we established a VPN. Here we see an overview how the infrastructure is organized in general. On the left side, there is a VPC which is connected with the internet. There it takes data from external services such as Google Analytics and saves them in the S3. On the right side, there is only a VPN connection with no direct connection to the internet. If this site needs data from the internet, it needs to be fetched by the left networks, stored in S3, and then you can work with it on the right side. The basic infrastructure, for instance, the VPC, the router, and the used routing tables are written in a CloudFormation template. The cluster and belonging resources for which, for instance, an EMR cluster is needed, are written in separated template. This template can be started as long as the basic CloudFormation template exists. Jenkins is used for scheduled data processing jobs. It creates a CloudFormation stack and adds the steps which starts the Spark jobs to process the data. After the last step has been finished, the previous created stack will be deleted. Core idea of using Jenkins is the orchestration out of the local network of the customer. Now let's take a look on collecting and loading the data into S3. Since the data should only be loaded to the cloud via push, we decided an on-prem method. For that, we set up an NiFi server in our own data center in order to transfer the data flexibly in the cloud. With NiFi, we are able to load the data in CSV and Afro format directly from the source system into the S3. If the data is in the cloud, we can do all the cool stuff with it. NiFi is very suitable for collecting data because it has multiple paired processors. The advantages of NiFi are the user-friendly web UI, being able to schedule every flow separately and no programming skills are needed. However, you are limited to the capabilities of the used processors. After the data is collected and loaded into the S3, we are able to process the data use case driven and make it available via SQL. We use Spark jobs to process the collected data and save it in Parquet format. For that, we add a step in an on-demand created EMR cluster. The advantage of Spark is the fast data processing. However, it needs to be implemented in code. With converting and compressing the data in Parquet format, we can save space, time, and money. When the data is converted and compressed, you need more CPU, but you save the time during the network transfer. Most of the time, this is a better choice because the network is often a bottleneck. Whilst smaller files need small space, with using services such as Athena, you only have to pay for the scanned data in store size. The data is loaded into the input layer and is stored by various criteria like partitions, purpose, sources, etc. It should be clear which kind of data you have to specify. It should be clear which kind of data you have at a specific level. This can be important when you need to reload the data because of corruption or for any other reason. Amazon EC2 spot instances are data backed up capabilities in the AWS cloud that offer a high discount compared to the on-demand pricing. You set a max bid price that you are willing to pay. When your spot instances start running, you pay the live spot market price, not your set bid price. You even can pay for several spot instances to save time by running bigger clusters. When the price goes over the max bid price, the spot instance will be interrupted by EC2 with 2 minutes of notification. After these 2 minutes, you lose all your data unless you managed to save the data within this time. To get rid of these negative aspects of the spot instances, you can run a hybrid Hadoop cluster mixed with on-demand and spot instances. With that, you don't lose your data, but just the replications and the compute power. For instance, you can use 1/3 on-demand instances and 2/3 spot instances. In case of losing the spot instances, you keep 1 copy of the data on the on-demand instances if you have a replication level of 3 and rack awareness configured accordingly. After processing data, we need to make it callable in Hive or Athena, for instance. For that, we use the glue crawler. The glue crawler scans the data in a subfolder, tries to classify every data according to the file type, and saves the schema in the GlueCatalog. We use the GlueCatalog as a Hive metastore on an EMR cluster or in Athena for ad hoc analytics. Sometimes numbers are too long for CSV serializer, deserializer, which causes an empty string in the relevant column. Another problem is that the default CSV serializer, deserializer is not able to recognize double quotes by default. If a field value is wrapped in a double quote and it contains a separated char, it will set the end of the field into the next field and all following fields are shifted by the one field. In this case, the crawler has to be set up in a way that, for instance, only new columns are allowed. Automatic updates are not welcome. Afterwards, every affected table has to be modified manually. Then it should work as desired. If you have trouble with carriage return line feeds in value fields, you should use other formats directly, which can handle this. No CSV parser is able to parse this in a clean way. For that reason, we decide to store the fields in Afro. Afro is used by NiFi either way. Currently, the reporting team is reaching the limit with the current infrastructure. Some reports need up to half an hour to send back a result. The long wait costs unnecessary time, and for that, personal cost too. After some research, we decide that Exasol could be a solution. Exasol is a high-performance, in-memory, massively parallel processing database, short MPB, designed specifically for BI, analytics and reporting. It can be used on several systems, for example, leading BI tools. Further, it is equipped with most of all JDBC drivers and can be used with the Hadoop ecosystem as well. Last, Exasol can be used to run Docker containers as UDF to run every type of code in any language. The purchase of a server and license for testing can be come very, Entschuldigung. The purchase of a server and licenses for testing can become very time consuming and expensive. For that case, the AWS marketplace is perfect. With an EC2 instance, with an EBS support, you can rent the license for the time of usage. This might look expensive for a 24/7 operation. However, you can test the software and terminate it at any time when you are not satisfied. Further, you are able to test various instances types to find a suitable setup, or can duplicate the instance to be more free in testing. In the first test, as part of a hackathon, we could reduce the query time to under 1 minute. Because of that, we will expand the test with Exasol. This will start shortly. At the beginning of the big data POC, we expired with decision tree and deep learning with Spark and Scala. We determined that it is difficult to scale the training and deployment of trained models. On the AWS Dev Days in Cologne, the Amazon SageMaker were promoted. Because of the hurdles of our experiments, we decided to give SageMaker a chance. SageMaker is a new tool which hosts a Jupyter Hub to develop, learn, test, and distribute the machine learning models in Python. After first tests, we can say that it has lots of potential. You can focus on the important tasks like training models and finding features. After choosing the infrastructure, SageMaker is doing the rest. Hopefully, in the near future, we can sense the advantages of SageMaker in our daily work. In the future, we want to combine Exasol with machine learning models created by SageMaker. We hope for better use experience and more insights into machine learning models for our reporting teams and belonging specialist departments. Now I pass the word to Manuel Marowski. Thank you for listening.
Yeah, well, first of all, also from my side, welcome to this webcast, and thank you to Roland and Matthias for an insight into usage of AWS and the experience by two of our customers. My name is Manuel Marowski, also a developer by Opitz Consulting, and I would like to give you a short presentation about our quick starter. Throughout the presentation, you may have thought, well, what I've saw looks quite interesting, and I want to try it out too. But how should I start? Especially for this case, we by Opitz Consulting developed a quick start using AWS resources to provide an easy opportunity to start with big data in AWS. If you've hooked you up after this presentation, please feel free to contact us, and we would be glad to help you out as well. Without further delay, I would like to start this part of the presentation with a short video of the showcase. Please don't be confused by German caption. I'll go into detail about each of the steps shown in the video during this presentation. Okay, so currently you can see the infrastructure, an illustration of the infrastructure, and here you can see the logical infrastructure. I tend to call it data flow because it shows which way the data goes, and I will go into detail in this in one slide. Currently, you see which parameter you can set in the CloudFormation template and in the AWS console to start the whole infrastructure. It's parameterized and it works very well. And just few adjustments you need to do, and it just starts here. You can see starting of the whole infrastructure in the console of AWS. Currently, you see the data warehouse offloading. Due to the low resolution, you don't see much, but actually what it does is just starting a script, which is automated by Uzi, and then the whole data of the SQL server goes into the HDFS and is stored there and is created by an external table you currently can see here. We used an external table with Hive, and so the end user can use query-like, SQL-like queries to query the data and get also results from the offloaded data. And yeah. So let's proceed. After you get a first impression, let me start with the contents of this part of this presentation. The presentation is divided into 5 parts. In the first part, I like to cover the main use case of the showcase, which is streaming analytics. The next part highlights the data warehouse offloading. I tell you what it means and what advantages it has. The third part is about the architectural overview and the technologies we used. Next is the data flow, which resembles the logical architecture. And then I'll go into detail about the parts shown in the video. Finally, I'll close this presentation with exemplary industrial use cases in which this quick start could be used and could be beneficial. The main part of the showcase is to process and analyze short messages, which can contain up to 280 characters. I'm quite sure that most of you know this service very well. It is Twitter. Maybe probably some of you used it already. We use Twitter microblogging service as a source for analysis. After the data from Twitter has been pre-processed, it is analyzed by a machine learning algorithm to determine the author's mood. On the one hand, these analyses are stored in a data lake. On the other hand, it's also displayed in a heat map on a dashboard in Kibana. All this is done in real time. Moreover, the goal is to enrich this data, the analyzed data, with existing data from the data warehouse, which leads us to the second part of the showcase I would like to talk about next. In this picture, you can see a typical simplified architecture of a data warehouse. There are various sources that provide data. The data is stored, cleansed, and harmonized in an integration layer. In the enterprise layer, business rules are applied. In the highest layer, which is the user view layer, data is prepared for queries by end users. As already mentioned, this is quite simplified architecture of a data warehouse, which can be found by in different variations by various customers. With the data warehouse offloading, a new intermediate layer to the integration layer has been introduced. This layer stores historical data which is not used regularly, into the refined data lake. The data is still available for end users and can be combined with data in the data warehouse. Some of you may ask, why should I use data warehouse offloading? Why it's so useful? To give you a suggestion to answer this question for yourself, I would like to point out 2 advantages of the data warehouse offloading, which could also apply in your current situation. First of all, cost can be saved by outsourcing data from an expensive data storage to a more cost-efficient. Especially in AWS context, S3, as we already heard from Roland, could be a sufficient solution. Second, it offers possibility to easily link the refined data from the data warehouse offloading with the unstructured data, for example, streaming analytics data, within the data lake. After I talked about what we did, let's just see how we did it. And to introduce this part, I want to talk about the technologies we used. Here you can see just a brief overview to give you a first glance. And of course, we are obviously short on time. I won't cover each point, but I like to talk about the major important ones. Every program we wrote is implemented with the programming language called Scala. That is the reason why the machine learning library which we used was SparkML, and we could easily combine it with Spark Streaming. This has greatly simplified the implementation. I just can recommend it. Kafka is the base platform for streaming, which I like to cover in the next slide. Other technologies such as Uzi and Scoop are used to automate the data warehouse offloading. Scoop handles actual offloading of the data, and Uzi is just for the scheduling of these jobs. From the whole list, it should be emphasized that everything is provisioned by AWS. And we use resources like EC2 instances, EMR clusters, as well as the Elasticsearch service, which are, as I already mentioned, totally automated with this CloudFormation template. You just need to provide some parameters. And to show you more about this architecture you probably eagerly waiting for, let's just continue with the next slide. As you can see in this picture, the showcase is supplied by two sources. On the one hand, Twitter, and on the other hand, an API that serves as a source for our data warehouse. This data is routed via the internet to our own virtual private cloud. The tweets are sent to Kafka via Kafka Producer, where the data is also preprocessed. A consumer receives the tweets and applies the machine learning algorithm to it. The processed data is then stored in our data lake and sent to a Logstash server for visualization purpose in a Kibana dashboard. Nginx was just used to establish the connection between the virtual private cloud and our Elasticsearch service. Maybe it's not required anymore, but we had to do it because otherwise we wouldn't get a connection, get these two resources working together. The Kafka broker, which is just called Kafka in this example, was installed on different EC2 instances, and we created our own cluster not using EMR. The MySQL is just a representation for our data warehouse, and it's also in a different virtual private cloud and installed with the default resources and an EC2 instance. The data lake, which is divided into refined data lake and the unrefined one, is based on just a simple S3 bucket. And after you get first glance and understood the architecture, the technical architecture, I would like to talk about the data flow or the logical architecture. You should already quite familiar with this picture. It just resembles the picture we already have saw already, and it's divided in such a way that the two use cases are clearly separated and presented. The upper part describes the data warehouse offloading, and the lower part the streaming analytics. Both parts are connected by the data lake. Let me first describe the data flow for the data warehouse offloading. The source data is provided via an API and stored in our database server on a regular basis. A scoop job, which is automated using USI, offloads the data into HDFS. Due to an external table in Hive, you already saw in the video, you can write queries, just like regular SQL, just called Hive query. HiveQL and you can write queries and the end user can use it. Since the data in HDFS is deleted or just AWS specific configuration, so when an instance is terminated, the data in the HDFS is deleted. So we store the data, we make a backup of the data in S3. Now let's go on with the streaming part, the second use case. A Twitter API provides the tweets in JSON format. These tweets are preprocessed in a Kafka Producer. After the preprocessing, the data is then sent to the broker. A consumer takes the preprocessed tweets and applies the machine learning algorithm to them. Depending on the analyzed mood, a numerical value between 0 and 1 is assigned. The analyzed data is then stored in our data lake and also sent to a Logstash server. Finally, data is visualized and on a Kibana dashboard in form of a heat map. Now that you have also understood the logical architecture, you're probably wondering when I can use such an architecture or in which cases this could be beneficial. For this case, I would like to talk about next. Here are just a few examples where this architecture could be used and just exemplary industrial use cases. For instance, predictive maintenance is a technique designed to determine the condition of in-service equipment to predict when maintenance should be performed. Use our example to provide a platform to process the data of in-service equipment in real time. Second, the real-time error detection is a production process. It's used to uncover errors in the production chain that would not be noticed at all or only at the end of the production process. you could already also use our example to process the data along the production chain and then process it. Dynamic evaluation of component quality is some kind of acceptance test of supplied components by some suppliers. When new component, for example, when new components reach the manufacturer, acceptance tests are normally performed to ensure the quality of the supplied components, but you can't really test every component. You use just a sample. So since not all components can be tested, defective ones could also be accepted and also be used later on. With our architecture like the one I've presented, you could implement an acceptance test that tests each component during the process. So you won't accept faulty components at all. And what you get is more accurate billing and also avoiding processing faulty components. Well, of course, this is just few examples and just a minor selection of examples, but it has one thing in common: the requirement for an architecture that allows a large amount of data to be stored and analyzed in real time. So this brings me to the end of the presentation. On behalf of my colleagues, I want to thank you for your attention. And if you may have questions, please don't hesitate to reach out to us, and we would be glad to help you. Thank you.